Section: Introduction. In this section, we discuss the challenges and advancements in large reasoning models, LRMs, like OpenAI's O1 and DeepSeek R1, which have made significant strides in mimicking human-like slow thinking. These models can slow down their reasoning to tackle complex problems that require deeper cognitive processing. They are trained using reinforcement learning to manage this slow thinking automatically. However, we question whether this automatic slowing down is reliable. Humans typically start with fast thinking and switch to slow thinking when faced with difficulties, allowing for efficient reasoning. While LRMs show some similarities, they often struggle with overthinking or underthinking due to their limited ability to transition between fast and slow reasoning effectively. To address this, researchers have explored two main strategies for scaling LRMs during testing. 1. Parallel scaling, which samples multiple answers and selects the best one based on criteria like consistency. 2. Sequential scaling, which tackles overthinking and underthinking by stopping reasoning early or encouraging continued reasoning. For instance, one approach limits the number of words during fast thinking to reduce overthinking, while another adds a wait token to extend slow reasoning. However, the optimal timing for these transitions remains unclear. To improve this, we propose ALPHAONE, a method that universally modulates reasoning progress. We introduce the concept of an alpha moment, where the thinking process is adjusted by a factor throughout the generation. Specifically, we add the wait token after certain structural markers based on a probability that changes over time, promoting slow thinking initially and then transitioning to fast thinking. Our findings from testing 3 different ALPHAONE models across various reasoning tasks reveal several insights. 1. Starting with slow thinking before switching to fast thinking enhances reasoning performance, which contrasts with human thinking patterns. 2. Slow thinking can lead to more efficient reasoning, as it reduces overall token length while improving the quality of reasoning. 3. Frequent transitions to slow thinking yield better results, as we found that adding wait significantly more often than previous methods led to improved outcomes. In summary, we highlight the importance of dedicated strategies for managing reasoning transitions in LRMs to enhance their performance in complex reasoning tasks. Section Summary. In this section, we explore the capabilities of large reasoning models, LRMs, in achieving human-like slow thinking through a novel approach called ALPHAONE, which modulates reasoning progress by dynamically adjusting the transition between slow and fast thinking. Our findings indicate that initiating with slow thinking enhances reasoning performance, suggesting that dedicated test time scaling strategies are essential for optimizing LRM reasoning. Section: Slow Thinking Transitioning. In this section, we discuss how we can utilize human-like slow thinking to tackle complex reasoning tasks. Our approach involves O1-style language models, LRMs, that can switch between fast and slow thinking. Specifically, during the reasoning process, these models often produce tokens like wait, and alternatively. When these tokens appear, the models slow down their reasoning, allowing for immediate self-reflection and correction of previous thoughts. Thus, reasoning that follows these tokens is considered slow thinking, while the rest is typically fast thinking. We define the overall answer generation process as a reasoning progress that ranges from 0 to 1, where 0 indicates the beginning and 1 indicates the completion of reasoning. This progress reflects how far we are in solving the problem, rather than just counting the number of tokens generated. A progress closer to 1 suggests that the reasoning is more informative, and we can achieve this with fewer tokens, indicating more efficient reasoning. However, measuring the exact progress is challenging, so we base our understanding on reasoning velocity. We assume that the reasoning speed during slow thinking is slower than during fast thinking. Next, we explore how to modulate reasoning progress, focusing on 2 main components: the thinking phase budget and the scheduling of slow thinking. Our LRMs follow a think then answer approach, so we need to adjust the thinking phase budget accordingly. Additionally, we can schedule slow thinking within this phase, allowing for user-defined plans, such as starting with slow thinking before transitioning to fast thinking. This modulation can vary from minimal adjustments to frequent and extensive changes. We introduce ALPHAONE, a framework for modulating reasoning progress during test time scaling of LRMs. We first define the alpha moment, which is when the thinking phase budget is scaled by at least a factor of alpha, where alpha is greater than 1. We scale the average length of thinking phase tokens to this new length, and this moment does not signify the end of the thinking phase, as it continues afterward. Before reaching the alpha moment, we activate slow thinking by appending wait after certain structural delimiters. This activation follows a user-defined schedule, such as starting with slow thinking. We model this activation as a stochastic process, specifically a Bernoulli process, where the probability of appending wait is determined by a user-specified scheduling function. We find that using a linear annealing function is the most effective method for this purpose. Section Summary. In this section, we describe how our approach, ALPHAONE, enables large reasoning models, LRMs, to transition between fast and slow thinking to enhance problem-solving efficiency by modulating reasoning progress and scheduling slow thinking. We introduce a universal framework that allows for scalable thinking phase budgets and user-defined slow thinking scheduling, improving the overall reasoning process during test time scaling. Section. While an LRM significantly increases slow thinking through pre-alpha modulation, this extended thinking phase often exhibits slow thinking inertia, making it difficult to transition back to fast thinking. Notably, without post-alpha moment modulation, the LRM substantially reduces the likelihood of generating less than, think greater than. Furthermore, inserting a few less than, think greater than tokens does not effectively overcome the inertia, failing to fully restore fast thinking. Deterministic reasoning termination. After the $alpha moment, we guide $alpha1 to transition into fast reasoning by disabling further slow thinking. Specifically, any generated slow reasoning transition token, wait, is replaced with less than, think greater than, to explicitly mark the end of the thinking phase, reinforcing a shift to fast thinking before entering the answering phase. This deterministic termination strategy allows $alpha1 to conclude reasoning naturally and consistently, enabling more efficient test time scaling. In this section, we discuss post-moment modulation. We find that while a large reasoning model, LRM, enhances slow thinking through pre-alpha modulation, this prolonged thinking phase can create inertia, making it hard to switch back to fast thinking. Importantly, without post-alpha moment modulation, the LRM significantly decreases the chances of producing less than, think greater than. Additionally, simply adding a few less than, think greater than tokens does not effectively break this inertia, failing to fully restore fast thinking. For deterministic reasoning termination, after the alpha moment, we guide ALPHAONE to shift into fast reasoning by stopping any further slow thinking. We replace any generated slow reasoning transition token, wait, with less than, think greater than, to clearly indicate the end of the thinking phase, promoting a transition to fast thinking before we start answering. This strategy allows ALPHAONE to conclude reasoning in a natural and consistent way, leading to more efficient scaling during testing. In our experimental setup, we evaluate the reasoning capabilities of LRMs using 6 benchmarks across 3 categories: mathematical reasoning, including AME 2024 and Minerva Math, code generation, live code bench, and scientific problems, Olympiad bench. We report problem-solving accuracy as the average pass at 1% and the average number of generated tokens. For our base models, we utilize 3 open-source LRMs: DeepSeek R1 Distilled, DeepSeek R1 Distill Quen 1.5b, DeepSeek R1 Distill Quen 7b, and a larger model, Quen QWQ32b. We set a temperature of 0.6, a top P of 0.95, and a maximum token length of 8,192. We define alpha as 1.4 and calculate the average token length generated by an LRM on any benchmark by randomly sampling 10 test questions. In our baselines, we compare our ALPHAONE against the original LRM and 2 other training-free, test time scaling methods. The first baseline, base, is the original LRM that automatically transitions between slow and fast thinking. The second, S1, enforces a slow thinking pattern by adding about 2 wait tokens near the end of the reasoning phase. We apply S1 at test time without any supervised fine-tuning. The third baseline, chain of draft, COD, limits each slow thinking step to no more than 5 words, reducing the thinking budget. Our main results show that ALPHAONE consistently achieves higher problem-solving accuracy than all baseline methods across all models and benchmarks. Notably, ALPHAONE improves the 1.5 BLRM by 6.15% while reducing token length by nearly 14%, demonstrating its effectiveness and efficiency. Compared to other test time scaling methods, ALPHAONE still outperforms S1 and COD, with an average accuracy boost of 3.12% and 4.62%, respectively. Surprisingly, even though ALPHAONE allows for more reasoning without reducing the thinking budget, its average token length is only about 4.4% longer than COD and 21.0% more efficient than S1. In our analytic results, we explore different scheduling strategies for S/T. We examine 4 variants: a constant strategy that maintains a slow thinking approach, a linear increase that shifts from fast to slow thinking, an exponential anneal that transitions from slow to fast thinking, and a linear anneal that resembles exponential anneal. Our findings indicate that the linear anneal consistently yields the highest reasoning accuracy, supporting the idea that starting with slow thinking before moving to fast thinking is the most effective strategy. The exponential anneal also shows promise, but it may lead to less stable performance compared to the linear approach. Section Summary. In this section, we explore the impact of post-alpha moment modulation on reasoning in language models, highlighting that without it, slow thinking inertia hampers the transition back to fast thinking. Our experimental results demonstrate that our proposed method, ALPHAONE, significantly improves problem-solving accuracy and efficiency compared to baseline models, particularly through effective scheduling strategies that favor a slow-to-fast thinking approach. Section: Can moment scale the thinking phase budget? In this section, we explore whether the alpha moment can effectively scale the thinking phase budget. Our findings, illustrated in the figure showing alpha scaling, reveal that the alpha moment allows for scalable thinking phase budgeting, meaning that as we increase alpha, the average token length during the thinking phase also increases. However, we notice a trade-off between the optimal alpha value and reasoning accuracy. This suggests that simply increasing the thinking phase budget does not always lead to better reasoning performance, highlighting the importance of identifying the optimal alpha moment for satisfactory improvements. Next, we assess whether one scales more efficiently by introducing the Reasoning Efficiency Performance (REP) metric. This metric compares the reasoning accuracy of our method to a base model, normalized by the thinking phase token length. A higher representative indicates better reasoning efficiency. Our results show that ALPHAONE achieves a higher representative on most benchmarks, indicating a better balance between performance and efficiency. For instance, ALPHAONE outperforms COD by 6.62 points and S1 by 11.68 points on Olympiad Bench, and exceeds COD by 14.22 points on Minerva Math. We then investigate how frequently we should transition to slow thinking. ALPHAONE modulates this transition by sampling from a Bernoulli distribution. We explore the optimal probability for this transition by scaling it from 0 to 1. Our observations indicate that both extremely low and high transition frequencies yield poor results, similar to the careful selection needed for the thinking phase budget. However, we find that a wide range of probabilities generally leads to improved reasoning performance. We also question the necessity of post-moment modulation. While typical methods focus on slow thinking during the thinking phase, ALPHAONE incorporates a post-alpha moment modulation to encourage fast thinking. Our ablation study shows that relying solely on pre-alpha moment modulation is insufficient, as reducing it to a single operation significantly decreases performance. This is due to the inertia created by increased slow thinking. By employing post-alpha moment modulation, we ensure a transition to fast thinking, demonstrating the need for both slow and fast thinking in our approach. Finally, we discuss the emergence of large reasoning models, which aim for human-level reasoning. Starting with OpenAI's o1 in 2024, many models have adopted the thinking then answering approach. These models, like DeepSeek R1 and Qwen QWQ, utilize large-scale reinforcement learning to align with human preferences, often using a special end-of-thinking token to signal the output of a solution. Recent research has also shown promise in applying reinforcement learning during post-training fine-tuning. Section Summary. In this section, we explore the scalability of the thinking phase budget using different alpha moments, revealing a trade-off between optimal alpha values and reasoning accuracy. We also introduce the Reasoning Efficiency Performance (REP) metric to evaluate reasoning efficiency, finding that ALPHAONE outperforms other methods on various benchmarks, and we emphasize the importance of balancing slow and fast thinking transitions for improved reasoning performance. Section: Reasoning with Test Time Scaling. In this section, we explore reasoning with test time scaling, which has recently proven to be an effective approach for enhancing the reasoning abilities of large language models, LLMs, during testing. We categorize the main scaling methods into two types: parallel scaling and sequential scaling. For parallel scaling, the concept revolves around best-of-n sampling, where we choose the best option based on uncertainty measures such as self-consistency, reward models, or perplexity. Some research focuses on sampling at the sequence level, while other studies look at sampling at the token or step level, using methods like beam or tree searches. On the other hand, sequential scaling aims to improve or simplify the thinking process during the generation of a single answer. This method usually involves refining and revising the answers produced by the LLMs or incorporating external feedback. Recent studies have tackled the issues of underthinking and overthinking in LLMs by promoting and limiting slow thinking, respectively. Since parallel and sequential scaling can coexist without conflict, there are also hybrid methods that combine both strategies.